So in continuation with organic chemistry, we're going to be covering amines and amides. So the final organic molecules we're going to cover are amines and amides. In an amine, we can see here that the functional group really resembles ammonia, which, if you need a reminder, is basically just a nitrogen bonded to 3 hydrogen atoms. But instead, in an amine, we see that the nitrogen can be bonded to 1 or more alkyl groups. However, in an amide, they more so resemble an ester in the fact that we have on an N carbon, it's double bonded to an oxygen, but it's also bonded to a nitrogen that can be bonded to 1 or more alkyl groups. Now, compared to the other groups, amines are below alcohols and thiols in terms of our priority. But for amides, they're higher than our aldehydes, but lower priority than our esters and carboxylic acids. So we have to keep that in mind when we are going to be naming these molecules that might happen to have 1 or more of these functional groups present. But in terms of just amines and amides outrank amines in priority if both groups are found on the same molecule. So we're going to start with amines. Amines are organic molecules that derive from ammonia, and recall that ammonia is a nitrogen triple bonded to 3 hydrogen atoms. But instead, in an amine, the nitrogen atom is bonded to a maximum of 3 alkyl groups. Here's the general structure for an amine. We can see here that at each spot where there's an R, this can either be an alkyl group or it can be a hydrogen atom, either one. So typically, we associate amines with a very strong, quite pungent smell. It's often reminiscent of the smell of ammonia, if you can kind of imagine what that fragrance is like. And similar to alcohols, we have 3 different types of amines. So, in a primary amine, these are molecules where the nitrogen atom is bonded to only 1 other type of alkyl group. So I'm just going to use this R to represent an alkyl group. And then that nitrogen is also bonded to 2 hydrogens. In a secondary amine, our nitrogen is instead bonded to 2 alkyl groups. They could be different, and 1 hydrogen atom. And finally, in a tertiary amine, we have our nitrogen bonded to 3 alkyl groups. So there's absolutely no hydrogen atoms bonded to it in this situation. So now let's move on to naming amines. If amines are the highest priority functional group, then we are going to change the ending of the name to amine. Now, we might have an amine that has multiple carbon chains bonded to it, just like we saw in a secondary and tertiary amine. So in these situations, we want to determine which chain is the parent chain. And once you've determined that, that's going to be at the end, but for the other 2 groups, or 1 or 2 groups, we are going to include it as if it was a substituent group. So to indicate its position, we would write an N separated with a hyphen before we write the alkyl group's name. And that just indicates that it's attached to a nitrogen and it's not part of our carbon chain like we've seen before. And just remember, for the parent chain, we want to indicate which carbon it is attached to in our final name. Now, if we have multiple amine groups present on the same chain, then, just like we've seen before, we have to include a plural prefix. So those are like our di, tri prefixes. And finally, if there's multiple functional groups, and unfortunately the amine group is not the highest priority, then we just include it with the other substituent groups, and we'd say, we'd represent it with the word amino instead. Okay, so let's put our naming into practice. We're going to do 2 amine examples. We're going to start by drawing the structure for N-ethyl 2-butanamine. So first we see at the end that we have amine in the name, which means that the highest priority functional group in the structure is going to be an amine. And so we can just go ahead and draw the nitrogen atom in. For amine structures, I kind of like to draw the nitrogen first and then base the rest of our alkyl groups around it, because remember, we can possibly have up to 3 different alkyl groups. So, directly beside the amine, we see the word butane, which we know, since it precedes the amine directly, this is going to be our parent chain. Better yet, we see the number 2 in front, and this corresponds to the position of the amine. We're going to find our amine bonded to carbon 2 of our butane chain. So that's fine. Let's just draw that in. So here's our bond. This first carbon it's bonded to, just going to represent it with carbon 2. I'll just draw the rest of the chain. There's carbon 1, 2, 3, and 4. And there we have our complete butane chain. Now let's move on to the substituent groups. We see here that we have the word N-ethyl, and that's the only substituent group we have present in the structure. This indicates to us that there's an ethyl group, but furthermore, its position can be found attached to that nitrogen atom, not a part of our carbon chain. So I'm just going to go ahead and draw in our ethyl group here, and we have it represented. Now it doesn't say any other substituent groups. So first we know that this is a secondary amine because there's 2 alkyl groups bonded to that nitrogen atom. And also, since we don't have any other substituent groups, we can just go ahead and put in a hydrogen atom there if you want, just for clarity, to indicate that. So this would be the complete structure for N-ethyl 2-butanamine. Now let's move on to the naming example for the structure on the right. So what I'm going to do first is I'm just going to go ahead and count how many carbons I have in this main parent chain. There's 1, 2, 3, 4, 5, 6, 7. The parent chain is 7 carbons long. So that information is going to come in handy when we're naming it, right? Now let's identify these substituent groups. First, we see here that we have an amine group, another amine group, and if you look at the end here, we also have a double bond, which also counts, as a functional group. So in terms of priority, we want to know which group here has the highest priority. And in this situation, the amines have higher priority over a double bond, which is the case for most functional groups. Double and triple bonds have pretty much the lowest priority. And so amine is going to be our ending. Now, we have to number the parent chain such that our functional groups are assigned the lowest possible carbon number. Now, I know it's tempting to assign this as carbon 1 because we have a functional group there, but remember, it's not our highest priority, so that's going to mess up how we number it. We actually want to start numbering from which amine group is going to have the lowest possible carbon number. And that will happen if we start numbering left to right. So then this amine would be found at carbon 2. This amine would be found at carbon 5. And now our alkene group, or double bond really, is going to be found attached to carbon 6. So remember, we want to number the carbon chain so that our functional group of highest priority has the lowest carbon number. So now we can kind of go ahead and assemble this information. I'm just going to write the parent chain prefix for 7 carbons, which is hept first. Now I'm going to indicate the position of my double bond, which is at carbon 6. I'm going to write that ene to represent that there is a double bond present. And then we want to indicate the position of our 2 amine groups, which is at carbon 2 and 5. And remember, since there's multiple amine groups, we have to include a plural prefix, which is di in this situation, and then end it with the word amine. And so the complete name for this structure is hep6-ene-2,5-diamine. So amines have nitrogen atoms, and nitrogen atoms have fairly high electronegativities. So they're going to exhibit those stronger intermolecular forces. I'm going to draw out the three different types of amines. So in a tertiary amine, we have our nitrogen has been bonded to possibly three different alkyl groups. All the hydrogen atoms have been substituted. So these R's are really going to be alkyl groups. So we're only going to have those NC bonds. So in an NC bond, it's a fairly high difference in electronegativity. So the highest intermolecular force we're going to have are dipole-dipole forces. We're not going to have any hydrogen bonding though. There's no hydrogen, so the difference in electronegativity just isn't high enough. But if we look at a secondary amine, well, now we see that we have, two of the groups are still alkyl groups, but one hydrogen still remains. And if we look at a primary amine, then we see that we have only one alkyl group and the nitrogen is bonded to two hydrogens. So in a secondary and a primary amine, there is going to be hydrogen bonding. And we know hydrogen bonds are the strongest intermolecular force. So the bonds in a primary and secondary amine, we can expect to be stronger than the bonds of a tertiary amine. So these molecules, they're also considered to be polar. So amines do have pretty high boiling points, but they're going to differ depending on what type of amine we have. Typically, with an amine of the same size, we'll see that primary amines have the highest boiling point, followed by secondary, because they have, one less place for hydrogen bonding than a primary does. And then the lowest boiling point would be of a tertiary amine. Now, amines are associated with a strong, pretty foul smell, and it's been found that a lot of amines are actually considered to be carcinogens as well. So now let's look at some amine reactions. In order to synthesize a primary amine, we have to have a reaction between an alkyl halide and ammonia. So here's our ammonia atom. And here's the alkyl halide that I'm just going to use for this reaction. So if you see at the site where the halogen is on that alkyl halide, and at the site where there's one hydrogen, it's essentially going to be the spot where kind of this alkyl group will attach to the nitrogen atom. So in our products, there is now our group. And this reaction is also going to form a hydrogen halide, which in this case was just hydrogen iodide. So if we want to keep going, we can actually synthesize a secondary and tertiary amine as well, if we just keep reacting them with more alkyl halides. Let's just keep using the product we have up here. We'll react it with that same alkyl halide. So remember, look at that site where that halogen is, and then a site at where there's one hydrogen atom. In the products, that's a site where the alkyl group is going to attach. So now there's only one hydrogen left, and now we have one alkyl group, and a second alkyl group, and again it forms a hydrogen halide in this reaction as well. And if we keep going, we can actually form our tertiary amines from our secondary amine. So here's our secondary amine. We'll react it with that same old alkyl halide that we used before. and at the site where the halogen is, and at the hydrogen, they will attach, and that's going to form our tertiary amines. Sorry for those squished alkyl groups. But those are going to be our products. So just to recap, we see that ammonia plus an alkyl halide will produce a primary amine. A primary amine plus an alkyl halide produces a secondary amine. And a secondary amine and an alkyl halide will produce our tertiary amines. So up next we have amides. Amides are very similar to esters. In fact, here's the structure of an amide, and on the right here I'll quickly just draw the structure of an ester. So in an amine, they're still composed of that carbonyl group, which is that C double bonded to an oxygen, but now that same carbon is instead bonded to a nitrogen atom, which is in turn can be bonded to either an alkyl group or a hydrogen atom. So we can form amides through a reaction between a carboxylic acid, which is where this carbonyl group is going to come from, right, Ca to represent carboxylic acid, and with an amine, which is where our nitrogen comes from. And just like amines, there's 3 different types of amides. In a primary amide, here we see that our nitrogen atom is going to be fully bonded to 2 other hydrogen atoms. In a secondary amide, our nitrogen atom is now going to be bonded to 1 hydrogen atom and 1 alkyl group. And in our tertiary amide, we see here that our hydrogen atom, if you can kind of see where this pattern is going to be bonded to 2 potentially different alkyl groups. So when naming amides, if they're the group of the highest priority, then the ending of our name just becomes amide. The parent chain is going to come from our carboxylic acid, which, remember, is the part that contains a carbonyl group, and we're going to use its chain length to precede the amide part. And we also don't have to indicate the position of our amide group, as it's going to be located kind of at carbon 1. Finally, any alkyl groups that are attached to our nitrogen atom are named similarly to amines, where we have an N with a hyphen in front of it to indicate its position. Okay, so we're going to start with the amide naming example on the left. The first thing that my eye instantly goes to is that nitrogen atom that's in the middle of our structure. We also see that the nitrogen is bonded to a carbon, there's a bond there, that is double bonded to an oxygen. So instantly we know that this is going to be an amide group. That's going to be our functional group of highest priority in this situation. Now, first we want to identify the parent chain. If we look for the parent chain, we're looking for the carbon chain bonded to that nitrogen that has the carbonyl group, that double bonded oxygen, which is the part that also comes from our carboxylic acid. And if we look here, then it would be this carbon chain. This is going to act as our parent chain, so we're going to use its chain length as the prefix before our word amide to signify it is an amide. So if we count the chain length, we see that we have 3 carbons in this parent chain. So it's a 3 carbon long chain, which also means we're going to use the word propan to signify this. Now we're going to want to identify any substituent groups. Now, if we look here, we see we have 2 other alkyl groups bonded to that same nitrogen atom, but they aren't our parent chain. So they're now, just additional alkyl groups we still have to account for in our final name. So if I highlight the first group, we see we have an ethyl. And if I highlight the second group bonded to that nitrogen, we also have an ethyl. So in total, we have 2 ethyl groups present that we're going to account for. And remember, since they're the same group, we're just going to use a plural di prefix to indicate this in our final naming. So now let's take all this information and assemble it. First, we're going to indicate our substituent groups. So since they're bonded to the nitrogen, indicate their position with an N, NN because there's two ethyl groups. Then we would include the diethyl. Now let's put our parent chain's prefix, 3 carbons long, so it's propan. And then we put the ending for the functional group with the highest priority, which is amide. So there we go, that's our final name, N,N-diethylpropanamide. Now let's do the example to the right. We're going to draw the structure for 2-bromobutanamide. Now let's kind of work this name backwards. If we look at the very end, we see we have the word amide here, so we know our functional group of highest priority is an amide. So that's just going to be the first thing I'm just going to draw in. Start with our nitrogen atom, and then this nitrogen atom is going to be bonded to a carbon that's also double bonded to an oxygen. That is going to be the start of our parent chain. Next, we can find the length of our parent chain by looking at the prefix right before amide, which is the word but. And but is what corresponds to a 4-carbon parent chain. So here would be carbon 1 on our parent chain. Just going to keep going. This is carbon 2, this is carbon 3, and this is carbon 4. And that's our completed parent chain. And now we're just going to do any substituent groups present on that same parent chain. So we see we have the word bromo and a 2 before it, so we have 2-bromo. This indicates that there is a bromine group present at carbon 2 on that parent chain. So if we look at our little numbering system down here, at carbon 2, I'm just going to draw a bond to bromine. And there we actually have the completed structure for 2-bromobutanamide. Now let's look at amide properties. Amides are very polar molecules, and this is because of the strong intermolecular forces that exist from their carbonyl group and the possible hydrogen bonding that can occur between the nitrogen and the hydrogen atoms. So, amides all have high boiling points, but if we're going to compare amides of the similar sizes, then we would see that primary amides have the highest boiling point. And this makes sense, since if we look at a primary amide, we see here that they can form 2 bonds with hydrogen, and that's 2 possible spots of hydrogen bonding, which is 1 more than a secondary amide and 2 more than a tertiary amide, which makes them way stronger than the other 2. Secondary amides would have the second highest boiling point, and then of course the lowest would be tertiary amides. So finally, as we increase the carbon chain length, similar to other organic molecules we've seen, the solubilities of these molecules will decrease. So for amide reactions, we can form amides through a condensation reaction between carboxylic acids and a primary amine, secondary amines, or ammonia. Depending on what we react the carboxylic acid with, we're going to end up with a different type of amide, pretty similar to our reactions to form amines. So here's the 3 I'm going to go through. If we were to react our carboxylic acid, here's just a generic example of one, with ammonia, which is fully bonded to hydrogen atoms, then we would end up with a primary amide. Here's our parent chain from the carboxylic acid, and here is where our nitrogen would bond to the carbon at the site where the hydroxyl group used to be. And so that's our primary amide. Through this process, we would also form water. Now, the reactions for the next two are pretty similar to the first one. If we were to react our carboxylic acid with a primary amine, where one of those hydrogens has been replaced with an alkyl group, then we would actually end up with a secondary amide, which I'm just going to draw out very quickly for us. So we see here now that we also have that alkyl group bonded to the nitrogen also present. And again, this reaction would form water. It is a condensation reaction. So finally, when we react our carboxylic acid with a secondary amine, so here our nitrogen is now bonded to two possibly different alkyl groups, then we would see that we would form a tertiary amide, where the nitrogen is now fully bonded to three different carbon atoms. It is no longer bonded to any hydrogen atoms. And again, we would form water during this process. And that is everything for amines and amides.